All right, so let me just share my screen. Okay, so today we are tackling the the topic of H2 mobility and how safe is it. So on today's agenda, so I am Noémie Bichon. I am project manager of the e-boost project, which I will be presenting a bit more. And I work at CARA, which is the European Mobility Cluster for Mobility Solutions of the Auvergne-Rhône-Alpes region. I will then give the floor to my colleague Thomas Crémaux, who is our expert in alternative energies, who will just make a brief introduction on H2 market and challenges. And we will then give the floor to Ceres Technologies. Julien Rullier first, who will present this company, and then our expert Amin Ghezou will present which demonstrations and which methods for which applications in H2 system safety. And then we will take questions and answers as mentioned. So without further ado, let me first tell you why we are doing this webinar. It's in the context of an EU-funded project, e-boost, which aims at supporting European electromobility SMEs through a range of services to strengthen their resilience, green and digital transformation, and internationalization. And we do this, as I just said, through a range of services, and the coming opportunities via the e-boost I will tell you the coming opportunities. So behind the e-boost project are 6 clusters. So networks of industries and SMEs from the mobility sector, so automotive and also rail and trucks. So from France, Spain, Italy, Netherlands, Germany, and Poland. So as I was saying, next e-boost opportunities, which I want you to put on your agenda. We will open a call for SMEs to join us in our Investor and Sponsors Day. So basically, it's an event where we are linking SMEs of the that are on the electromobility sector to investors and sponsors. And it will take place back to the Drive Forward conference, which is a conference and a fair dedicated to the decarbonization of the automotive industry. And we will also have a site visit to the TNO Powertrain Center, so a high-end research center. The call is not open yet, but keep follow us on our social media to not miss on this opportunity. Other coming opportunities are International Business Forum, which will be online. So it's an opportunity to make business cooperation with USA, Canada, Turkish, and European enterprises. And so it would be via the platform B2Match. It will probably be end of April or beginning of May, but the date is still to be confirmed. So again, make sure to follow us. And last but not least, there's another webinar dedicated to H2 solutions, which will be on the 18th of March at 2. And it's organized by our partner RAI ANL, which is a cluster, automotive cluster based in the Netherlands. And so, yeah, here you have the registration link, and I will be sharing the slides, so you can find the registration link there. All right, moving on. Let me just introduce you to CARA a bit more. So CARA is as I mentioned, is the mobility cluster of the Auvergne-Rhône-Alpes region, which is one of the main industrial regions here in France. We So yeah, here you have some figures on the automotive industry in the Auvergne-Rhône-Alpes, and our aim is to foster the economic development of those enterprises, and also to let's say pave the way for the transformation of the mobility sector. So as you can see here, working on components, critical material, of course working on efficiency, decarbonization, and digitalization. Decarbonization and digitalization are our main topics on which we support the companies in the region for the future. And it's across 6 industries, so automotive, truck and bus, river, aerial guided transport, rail, and micromobility. Okay, so without further ado, I will stop sharing my screen and I will give the floor to Thomas Crémou for an introduction on H2 challenges and challenges on the market. Thomas, the floor is yours.
Yes. 2 seconds. You hear me?
Yes.
Good. So, hello. Before introducing Amin, here are some elements about hydrogen in mobilities. Why H2 for mobilities? First of all, we know that hydrogen is a non-carbon molecule, so its combustion does not generate carbon at exhaust. That's why we can have zero emission vehicles thanks to hydrogen. It has high mass energy density, 3 times higher than gas oil. It enables autonomy. And finally, it helps electromobility through refueling via matter transfer instead of the low chemical reaction we have for batteries. 5 to 16 minutes for the refueling. These advantages make hydrogen useful for several uses. We know that hydrogen is not very relevant for light vehicles, except for taxi. But the part will be more important for heavy vehicles, as we see on the left, on the right graphs. And among these heavy vehicles, we have on-road engines and off-road engines. And we don't have to forget that we have a part of hydrogen forklift vehicles, which are already used since many years. 2026, I think. But hydrogen has several challenges. The first is it needs a complete ecosystem, production, distribution with pipe, refueling station, industrial and mobility consumption. It has a low chemical stability. As example, low emission energy, 12 times less than gas oil. So it has a chemical energy. Moreover, it has a physical energy because we have to compress it because of the low volumetric energy density at 350 bars, as example. And finally, the flame is not visible. The molecule is odorless, and the molecule is the smallest it can be possible, so we have micropermeability. So we have to have special processes in industry to manage hydrogen molecule. So with safety, I give the floor to Amin, which present us.
Yes. Thank you, Thomas. Thank you, Noemi. Do you see my screen?
Yes.
Yes, it's okay.
And I will put it in full presentation. Is it in full screen?
Yes.
Yes.
Okay, so maybe short introduction about ourselves, Julien. I'm Ingezu. I'm a safety leader on hydrogen and automotive application. I've been working several years on hydrogen storage systems, either on automotive, stationary, machinery, and transport of dangerous goods application. And actually, I'm a safety leader on fuel cell hydrogen systems, and I'm working in Ceres Technology and in the department of automotive of Julien Rollier.
Hello, everybody. So myself, I'm a safety expert on automotive embedded systems, and today at Ceres, I'm leading the automotive department. I will explain you quite shortly what do we do at Ceres Technologies. So Ceres is a medium company. We are 250 people, and we are working in a group that is called the Group Gorget, which dealing with industrial companies such as Excel Technologies that is providing submarine drones, mostly for defense, and Prodways that are dealing with 3D printers. And at Ceres and Eliatech, we are engineering companies. We, as I said, we are 150 people, and I don't remember the name. Our result in last year's is around 20 million euros. We are settled all over French territory, and especially in Auvergne-Rhône-Alpes region, in Lyon and Grenoble, but also in Paris and in the southwest of France, and also in Morocco since 2 years now. We are working with major companies and also most little company with startup and new stakeholder in innovative mobility solution. And with most of our customers, we are working on safety subject for electric or hydrogen solution, either on embedded systems or ground solutions. We are involved in different cluster and partnership. So Cara, of course, but also Pôle Véhicule du Futur and Automotive Engineer Society, Agrotechnopole for agriculture solutions, and EMDR, that is the Institute for Risk Management. So, I mean, it's your turn.
Yes.
Explain us how safe is it?
Okay, thank you, Julien. So now we will deep dive on the hydrogen topic to see what are the characteristics of hydrogen, what are the risks that are linked to those characteristics, and also what is the way to ensure safety of our projects and applications. First of all, a big picture about the value chain of hydrogen. We have different steps, different projects where we need to first product the hydrogen by electrolysis or other methods. Then we need to transport this hydrogen either by train, by trucks, or directly by pipings. And the objective is to achieve it to the end user. The end user could be linked to different applications, either industrial applications using hydrogen or mainly today around the table we speak about transport, cars, trucks, buses, trains, etc. So in each step here we deal with hydrogen, so we need to know what are the important characteristics of hydrogen to ensure safety. Here are some points that I want to highlight. First of all, we need to know that the hydrogen is the smallest atom in the universe. That makes it really that makes the risk of leakage present, because hydrogen will go through a very tiny, small breakage or a small path. So we need to be careful about the risk of leakage. Then the second characteristic is that the hydrogen is difficult to detect because it's colorless, odorless, and tasteless. And then we have a characteristic that is really important to know about hydrogen, is the flammability and explosivity range. Here in the picture in the middle, you can see that starting from 4%, which is the lower explosive limit, we can start having a risk of explosion or flame. And this goes up to 75%. This range is really large compared to other gases that we might use. Maybe an example in automotive, when we use methane or GNV vehicles, the range is 5 to 15% only. Up to 15, we don't have a risk of explosion anymore. Here in hydrogen, the range is really large. So some other characteristics to know. We have minimum energy emission that is required to init this hydrogen when it leaks. That is really low. 17 microjoule, maybe to give an idea, is the energy required for a snowflake falling. This is the image that we link to the energy that is required. So we will be careful on hydrogen applications about emission sources around our hydrogen systems. We need grounding, for example, of transport vehicle before fueling and defueling. We will try to avoid spark sources, etc., around our system. Last characteristic is about fragilization, and here we mean the compatibility of hydrogen. Hydrogen is not compatible with all materials. With some steels, it can create corrosion and damage the system and then leak. So we will be careful about the materials that we will use in our product with our suppliers. We will require raw material certificates to ensure hydrogen compatibility. So mainly these are the characteristics that we need to know about hydrogen to be able to identify the risks. So the main risk linked to hydrogen, regarding what I said before, the first one is the risk of explosion or jet fire. When the hydrogen leaks and some conditions are met, we can have an explosion or a jet fire. This phenomena is described by ATEX. There is an ATEX standard that describes that, and on the picture on the left, we have what we call the hexagon of explosion. It describes what are the conditions to have an explosion. When we have in the air hydrogen in gas or spray or something like that, in presence with the air at a proper mix proportion, the 4%, for example, and then in presence of ignition source, we could have we will have an explosion. There is a last parameter, which is the accumulation or the confinement, that is aggravating factor. On the right, just a picture to show what hydrogen jet fire could look like. This one is huge. It could be could be a pipe breakage, and this is a life situation that we could face in case of crash or drop of a system. There are some technical solutions that we need to assess from safety point of view, but for example, you have excess flow valves to avoid that this flow rate when you leak is too high. The second risk linked to hydrogen application is the burst. This one is not related directly to the characteristics that I've shown before. It's mainly linked to the fact that we transport hydrogen on pressurized gas situation, so up to 700 bars. So we need to be careful about the tanks to avoid the risk of burst. There are different causes that can lead to a burst. Mechanical wearing of the system, maybe by tank design issue, or misuse of this tank. What I mean by misuse is that using the tank with a flow rate to fill or defuel that is too high, that could lead to really low temperatures and high temperature inside the tank. This is something that can lead to fragilization of the tank and a burst. There are some life situations also that could be at risk for the tank, which is the risk of fire. If you have a localized fire on the tank, you could have also a burst. Regarding the external regarding the tank, there is also the topic of corrosion that could damage the tank and create weakenings. And the last element is overpressure. The tank is designed to work on nominal pressure, maybe to resist a little bit more, but we need to ensure that there is no failure on refueling stations. We need to ensure that there is mechanical barriers to not have a higher pressure value. There are some protocols, SIG 2601, for example, for the refueling station to ensure that we don't cross the limit of the tank. Also, we could have some overpressure issues with some failure of components that regulate the pressure. We have regulator and compressors in our system. We need to ensure that these ones will not fail up to create a pipe breakage or a tank burst. And then some other risks without deep diving on them, but important to know. The first one is the risk of anoxia. Anoxia meaning that being in an environment where you don't have enough oxygen or air to breathe. This could happen in closed area where you have hydrogen leakage inside a car, for example, if there is no ventilation. The thermal risk here is linked to some applications when we speak about liquid hydrogen applications, not pressurized gas hydrogen. We need to have the hydrogen at very low temperatures. In case of leakage, we could burn surrounding people. Then the last point is electrical risk. It's indirect risk, not linked to the hydrogen characteristics, but in our hydrogen applications, we have fuel cell systems, for example, that generates electricity thanks to hydrogen. So we need to ensure no short circuits and no electrocution of surrounding people. So this is a general overview of the risks that we have using hydrogen, but how can we ensure that at the end we have a safe product that we can commercialize? For that, there are methodologies, there are tools, and there is functional safety to help us to identify the risk and manage them. First of all, regarding this topic, one point regarding regulation and safety in hydrogen applications. There are several regulations that you could see on the left side Depending on the application domain, if you are an automotive application, you need to apply R134 GTR13. If you are on transport of dangerous goods, you need to apply the ADR. On stationary and maybe on machinery, the PED, etc. The list is not exhaustive, and maybe this could be an idea of a future webinar for CARA. But these regulations covers some design rules, some elements that we need to prove to have the homologation from the authorities. But it doesn't cover the complete risks that we could face that we could have on an application. To do that, we need to use functional safety standards that I will describe in details a little bit more after. But one thing, what's important to know is that if we want to have an homologated system and a safe system, we need to do both activity, regulation, and safety. So what is functional safety? We try to describe it by a process, which is identifying the risks, having a clear description of them, having a rating also. Not all the risks are dealt at the same level. Have mitigations in front of each risk, and validate the fact that these mitigations reduces the risk. In the picture in the middle, you can see the representation of what the probabilistic approach of the functional safety, where we consider that there are risks that are non-acceptable and acceptable. What is an acceptable risk is a risk that could be really probable with high frequency, but that could have a really low severity. We could also have risks that are acceptable if they are really severe, but they don't appear at all or at really low frequency. Then in other cases, we have a risk that is not acceptable, and we try to reduce this risk by putting protection or prevention control measures to come back to the acceptable risk. The functional safety has two challenges or two aims. The first one is to ensure that the product that we are designing, that we are building, is safe. And the second objective is to provide evidences to the authorities that the manufacturer, the OEM, has done all the proper steps, all the proper activities to ensure that the product is safe. One element that is really important when we speak about functional safety is the robustness of the safety functions. And here we will speak about safety integrity level. The idea here is to say that not all the risks will be dealt and managed on the same way in a project. For example, if you pinch your finger in a window, it could be painful, but the impact or the damage will not be critical. On another case, another example is speaking about, for example, braking systems or steering systems. If you have a failure on those systems, the consequences could be really severe. So when we build a system, when we develop a system, we will not put the same efforts on different risks. The example that we have here in the picture below is speaking about a barrier. The objective of the two barriers is to avoid the risk of fall down there and being harmed. But according to the risk and the situation, for the left picture, we could say that the road is used by pedestrians, bicycles, that comes with low speed, and maybe not so much people use this road. So we will not put a lot of effort to put this barrier. We can agree that this is enough to have countermeasure to the risk of fall. On the left situation, If we say that this road is used oftenly by cars that has high speed, the wooden barrier is not enough anymore. We need to ensure that our safety barrier is robust enough to avoid the risk of falling down. Coming back to the hydrogen topic, since we say that we have a risk of leakage of hydrogen that could appear easily, since we say that the effect of this leakage could be explosion or jet fire, so high impact, so we will not put a simple manual valve to close our systems. We need to ensure that we have sensors, hydrogen sensors, pressure sensors, temperature sensors to detect the leakage. We need to ensure that we have the ECU that reads the information at the good speed and send the order at the good speed to a solenoid valve that has a closure and a timing characteristics. So this is about safety and integrity level. Coming back to the functional safety standards, we have here a list of different functional safety standards according to the application domain. Let's take an example of a hydrogen tank. According to if you use this tank on an automotive application, you will need to use the ISO 26262 to develop safety activities. If it's on stationary or machinery application, it's 13849. For railway application, you have the SENELEC standards, etc. We have different standards and different names and numbers here, but the approach is quite similar. The objectives of these standards are to define a common design and a common process to assess the safety of the system, and it also helps OEM suppliers, manufacturer to have the same references and the same language when we speak about safety. We have on the bottom side of the slide an example of how we rate the risks and how we define SEAL, ASIL, or PL function. SEAL is for safety integrity level, ASIL is for automotive safety integrity level, and PL is for performance level when we have some standard. It's the same approach. We need to define for each risk what is the exposure to the risk, to the hazardous events. Does it happen every day, or does it have a very low frequency to appear? Is it controllable? When the hazardous event appear, can we avoid the harm? And then the severity. If the hazardous event appears, does it create light injuries, or does a fatal injury can happen? When you combine these three parameters, you have what we call the ASILs that could go from QM, A, B, C to D. D is the last one. So, for example, if we say that a risk can happen every day, if we say that it's uncontrollable and unfortunately that has severe consequences, the ASIL will be D. And then on all the other situations, if we are able to prove that the exposure is lower, the controllability is better, and the severity is lower, we can have a lower ASIL rating. It's really important to define the SEAL or the ASILs at the good level, because one thing that is important to know when we speak about safety is that the SEALs has impact on both project and product. On project size, depending on the ASIL that you have, you will have impact on the activities that you need to do. If it's QM or if it's ASIL D, you will not have the same activities and deliverables. It will have impact on the planning of these activities that you need to provide, on the organization of the team also. You will need to have a safety manager on the team, to have an independent safety assessor that assess the deliverables. And in general, not only speaking about safety engineer or safety manager, the safety skills and the safety awareness of all the team members need to be adapted to the skill level that we have on our product. Then the impact on the product itself, because we have a high seal, we will define characteristics and requirements on the technical aspect of the component. We need better hardware, software, materials, etc. We need to deal with a supplier about safety activities. So there is supplier management that needs to be carried here, and at the end, cost impacts. One slide about what we call a safety plan. We wanted to give you an overview of the activities that needs to be done when you have safety topics on your project. This is a document that needs to be built in the beginning of the project to know what to do, who does the activities, and when. General overview on the chapters. You need to define the safety organization of your program. What are the role and the responsibilities of everyone? How the meeting will be done. Having a clear description of the technical project, the scope, the PNID, for example, when we speak about the hydrogen systems, the architecture, the standards that we need to apply. Then the step 4 on the top, the picture is bigger. It's because here we have the list of deliverables. The list is not exhaustive, but here you will hear documents, names like item definition, HIRA, hazardous, so to identify the risk and to assess them, FMEAs, the process, system, design FMEAs, and then some specific deliverables that maybe we don't use. We are not used to do them in automotive applications, but here I mentioned ASOP study. This is a methodology where we deep dive on fluids behavior and how the failures could happen on the fluid, which is our hydrogen. And ATEX study. ATEX study, I mentioned before, the standard that describe if you have a risk of creation of an ATEX zone on your system. Without diving too much, you need to have a validation plan. You need to focus on software activities if you have software in your scope. Then all these activities and deliverable needs to be assessed by confirmation measure. So you need to do confirmation reviews on all the deliverables, and you need to have a global safety assessment on your program. Of course, all these steps need to be described in a planning that fits with the project planning. If we do that 2 years after the SOP, it will not be useful. We need to ensure that all these activities reach the global project milestone. We arrive at the last slide of the presentation. Maybe Julien, a few words
Yes.
about the safety and cycle.
So on this slide, what we want to show is that dealing with safety is mostly dealing with engineering requirement. So we wanted to make a focus on the product requirement on the left side. We have on the top left the vehicle or system requirement, and we will identify some important risk we have to deal with, and we will have a top-down approach to cascade the requirement. So from the vehicle level through system level and subsystem level, and stop at the component level. So for example, if we are dealing with a hydrogen storage system, we will identify a risk of fire explosion, and we will have some requirement on the safety mechanism that will allow to reduce the risk concerning some leaking problem on the system. And at the bottom of the V-cycle, for example, we will have some requirement on components such as solenoid valve or temperature sensor or other sensors that are critical for safety. So once we have all the requirements on the left side, we have to integrate them in a system and a vehicle, for example, or a stationary system. It's the same approach. And we have to validate step by step and go up. So on the right side, this is the integration, verification, and validation phase of the life cycle. And there should be a perfect matching between the requirement on the left side and the validation requirement on the right side. And we are compliant with a system that is validated when every requirement on the left side has been checked, and we are sure that it will work as we want regarding the performance, regarding the response time, for example. And we are sure of it because we have made a verification or a test that will demonstrate the confidence level we can have on this requirement. So this work for mechanical requirement, but also electronic hardware, software requirement, and so on. So it's an important activities that to define the requirement on the left side, it's the product design, and also a major activity on the right side to validate the system. And at the end, mostly on functional safety standards such as ISO 26262 or other, this is mandatory to have an assessment activity that will be done by an independent body, an independent company, or an independent person. It depends on the activity sector. For example, in railway industry, you have to assess your system with an independent body, such as Certifair or TÜV or other independent bodies that are accredited to do it. In other industrial sectors, such as automotive, you don't have to do it with an independent company, but you have to do it with an independent person that has not been involved in the project. I think that's it on this slide. So yes, and what we want to share once again is that what will be the safety process will allow to have a safe product and also to have the demonstration that the product is safe. So it's a matter of design, of safety design, firstly, but also a matter of give the evidence that the design is safe and be able to prove, to give this evidence to a regulator, but also in case of incident or accident during the lifetime. So thank you very much for your attention, and we will be pleased to answer to your question. I saw at least one question in the chat.
Yes, indeed. Maybe Samim, do you want to take the floor and ask your question directly? Samim Ghafouri.
So, well, I think I understand the Samim question. The precautions between mobile and stationary application may be the same in a qualitative way. What could be different, and it's not because it is stationary or a mobile solution, it's the way the catastrophic event could appear. And the questions that we will ask are always the same. And this is, what is the exposition of the catastrophic event, of the hazard? We will ask how many people are around the system, what will be the severeness of injuries, is it possible to keep people during the catastrophic event, and also for the people that are involved, how can they control the situation? Is it possible for them to go away, and so on. So it's not specifically a matter of difference between mobile and stationary, but a matter of what we call the use case or the life situation of the hazardous event.
To give an example, Julien, according to the risk and the people that are exposed to the risk, we know that in railway there is the topic of maintenance that is more present than in automotive, for example. We need to do hydrogen leak checks more regularly. This is a way to cover the risk because we expose more people to the risk of leakage. The risks are the same, but then the technical solution needs to be adapted to hazardous events and to the exposure.
As a caricatural example or extreme example, you can have a big explosion, but if there is nobody around the system, in fact, there is no risk and no need to have any seal approach. Maybe someone has another question about our presentation or something else we didn't present on hydrogen safety. Do we conclude that it was perfectly clear?
It was indeed very clear. Thank you very much to both of you. So I see here we can find you on your website and via email. So I guess participants are free to send you an email if they're interested in getting in touch with you.
We'll be happy to discuss this hydrogen safety topics with you.
Perfect. So
thank you once again to everybody to be there with us today. And I hope we will see you soon. I let you, Noémie, if you want to conclude.
Yeah, no, that's it. Thank you everyone for joining us, and of course, thank you again, Amine and Julien, for your, and Thomas for your. It was really clear, even for me, who I'm not an expert. So thank you so much, and okay.
And have a nice end of week and weekend.
Thank you.
Thank you.
You too.
Thank you.
Bye-bye,
Bye.
everybody. See you.
Thank you. Bye.